So each year when we run this class, I choose a different molecule. And this year, because we got such a big class, I figured I should choose one which has got a number of different syntheses, I guess, published. So in the Moodle, I'll distribute some different papers, which your group can decide which one they want to do. Basically, it'll be first come, first serve. But there are other ones out there in the literature. So if you're not particularly impressed with any of the ones which I've distributed, you can choose one of the other ones. So this particular synthesis is from William Johnson's lab in 1975. So I guess in a way, there was sort of a golden age of synthesis, which has passed us, mainly because the way that research funding is doled out, well, at least it sort of died in Canada to a certain extent. It's basically by the way that the research funding is doled out for basic research. One of the fascinating things about synthesis itself is that, and particularly if you do it, is that you get exposed to a whole bunch of different reactions. Did you have a question? Okay. Whereas if you're working on a synthetic methodology, you tend to be doing a similar reaction over and over and over again and optimizing it. There is certainly benefit to that. But if you're doing a total synthesis, you come across, there's a whole bunch of little hurdles to complete, and you get the breadth of chemistry you can do is quite extensive. So it's part of the, and then often you come across a problem which you need to solve, and then basic science gets done there. So it's something which, I don't know, I just fell in love with because I think it's just great. But anyway, this is an old paper, 1975, and there are certain reactions which we'll talk about that there's certain steps that we could improve upon based with some of the newer methodologies that we have. But I thought we would just do this one, and it's quite fascinating. Now, so typically, where's the next slide? PowerPoint. Fun. So the way I would normally do this is I would give you a nice background as to why this molecule is important to do a synthesis on. I'm basically going to leave that out so you guys can do that when you do your presentations, since it'll be on the same molecule. I've tried to draw this in sort of 3D and a skeletal structure that's looking at it from, say, the top down or basically the side view. So it's an interesting...
Sorry, is that methyl group on the left one, is that attached to the top ring or the double bond? The left side. Methyl group, very bottom.
This one? This one?
Yeah, it looks like it's attached to that double bond, but I'm guessing it's supposed to go behind.
It's behind it, yes.
Okay.
So over here, it's basically attached to... Does my little laser pointer work?
Yep.
Okay.
I can see it.
It's attached to that carbon there, so that's a quaternary carbon right there. So yeah, it's behind this double bond. So this is a interesting molecule in a number of ways. It's got a 7-membered ring here, which is fused to what we would call a bridge head carbon here. And then there's a 5-membered ring and a 5-membered ring, which make up a 6-membered ring. So bicyclic, now it's actually a tricyclic compound. And it's, the other thing that you'll immediately notice is that it's all carbon and hydrogen, right? There's no other functional group. So it's basically an alkane with an alkene attached to it. There's a couple of places where we've got, like this is a quaternary carbon, some interesting stereochemistry. So yeah, it's hard, like this diagram on the right, it's kind of very difficult to like view things properly. So from when we get to the stage in the synthesis, I'll basically just be using the diagram on the left. So we're looking at it sideways. And drawing it this way sort of also shows some of the way that the three-dimensional structure of it is, and like which part of the molecule might be sterically hindered, like hindered, and which side might not be, that type of thing. So, well, when we get to that stage, I will do that. I'll turn off that part. So the next thing I would do is basically describe the retrosynthesis that the group approached. But because this is a class, I'm not going to do that, but I'm going to ask you, what are the challenges in synthesizing, at least what do you think are the challenges in synthesizing this molecule here?
First thing I think of is that like it's not exactly easy to get like bicyclic structures, let alone tricyclic. Like,
okay. What else is interesting or difficult?
There are no like functional groups, like well,
Yeah,
other than like a double bond.
no, I'll put in quotation marks here, real functional groups. Okay, so this can be a benefit and a curse, right? So the curse is, how do you make the bonds? What could potentially be a benefit, though?
You could use a lot of methods that are like sensitive to functional groups.
Right. So there's, yeah, there's, if you don't have a lot of other functional groups, you don't really have to worry about potential side reactions. So, yeah, so you've got your arsenal of reactions is larger because you don't have to worry, because there's no other functional groups. You don't have to worry about things going wrong. So the benefit is you could have there's I'll just put less side reactions.
well, and the molecule's pretty hydrogenated, I guess would be the right word. Like,
Saturated?
yeah, that's what I was actually looking for.
Right. So yeah, so there's a good chunk of this molecule which is unreactive. Okay, so any other potential challenges in how to what are some other problems?
I mean, my big thing is I don't understand how you coax these carbon chains into these rings.
Okay, so yeah, how do you
back to the first thing I said, kind of.
right? And so you've got, and one of the other points which is typically very difficult to do is that you've got a carbon here, which will be chiral, which has bonded to 1, 2, 3, 4 carbons. So you've got a quaternary carbon, this is often very difficult to do. So I'll just put quaternary carbon. So that can be a challenge. And so Right. So the other nice thing about this when it comes to the retrosynthesis, the various papers which what people can choose from, a lot of them do this slightly differently. So which bonds to break and which bonds to make. So in our case, the two bonds that are going to be which are going to be broken in the key reaction are this one and this one. So we're going to make a 6-membered ring, 1, 2, 3, 4, sorry, a 5-membered ring, and the 7-membered ring in the same step. So this is going to be these two bonds here are going to be broken, and this long chain is going to be tethered to the rest of the reaction, the rest of the molecule. So that's the key step here, is going to be the breaking of this bond. Okay, now if you've got an alkene as your sole functional group here, what can alkenes be converted into and back again from, which could be more useful to us? So so alkenes can, there's a whole series of reactions which alkenes can do. Like Markovnikov addition of HBr, or make dibromides or epoxides or all these sort of things. But alkenes can be converted into, like, for all of the reactions that we basically were just doing, like aldol reactions and Claisen condensations and all of these sort of things. What we were relying on then to do the chemistry was basically we needed a carbonyl. Because the carbonyl's got the interesting sense that the alpha carbon can be a nucleophile and the beta carbon can be an electrophile. So what we're going to see is that this carbonyl, we're going to have a carbonyl here, and basically making the alkene is going to be the last step in the synthesis. So, but we're going to rely on some carbonyl chemistry here. Actually, I think that's
like, is the 7-member ring getting cracked instead of the other 5 because it would be like lower energy to break it? Or
so it's going to be yeah, we'll get to that. We'll get to that. Okay, so like if you want to convert an alkene to a carbonyl, there's a couple of different reagents we can use. The one I think of off the top of my head the most is ozone, right? You can break that. To go from a carbonyl to an alkene, the reaction I think of most often is the Wittig reaction. It turns out that they don't use either of these steps to do that, but they'll do something else, and we'll see that a bit later on. But anyway, I wanted to get your sense, like when I look at just a molecule which is all carbon atoms and very little other stuff, to me these are the hardest kinds of things to get creative behind and design a synthesis for. So it's quite interesting. All right, so let's go on to the next part here. Oh, I better clear all these diagrams. I think PowerPoint's got a drawing thing. I should try to use that. Oh, good. I think this is it. All right. So this is where the synthesis starts. My question to everybody is, how do we make this starting material here? What would be some ways that we just looked at which we could make this compound here? And this paper was, it doesn't actually describe how they made this starting material. This is where they started from in their synthesis. They would have published the they said they grabbed this from paper Y or whatever it would be. So, but I didn't look it up. But I was just thinking, if you had to make this, what would be some ways that you could do this from relatively simple starting materials?
Is this an enolite?
Okay. So let's see here. So breaking this bond right here. And what are you going to react it with? So we need something which has got 3 carbon atoms, right? And we need this to be an electrophile. So if we did an aldol reaction with acetone, let's move up.
I hate this because that's what I was gonna guess,
Ah,
but I didn't have like a reason behind it.
okay, so this gets protonated to here, and if you leave it long enough, you'll get the E1CB and it will dehydrate. So I wonder if it's just as simple as that. Sometimes it's difficult. Yeah, so it could be something as simple as that. That's what I probably suspect is going on.
It seems like a nice cheap way to make it, anyways.
Right. Now, the only thing which I could think of which would be slightly difficult is, yeah, you'd have to control the way that you do this aldol reaction because there's some possible side products to it. Okay, good. Now I'm gonna erase all this stuff. Next question. What do we remember? I guess I should have hidden what the product is. What do we remember about organic copper? Okay, so let's see here. Pen. Let's do red. Let's pretend I had that same big R group and I used magnesium bromide. So the Grignard reagent for this is step 1. And then step 2, I use the same acid chloride. What product would I get here? So Grignard reactions or reagents, they 1, 2, 3, 4. Grignard reagents tend to react 1, 2, so they'll directly attack a carbonyl. Whereas if you've got an organocuprate, the R group attacks the 1,4 position, and then these electrons move here, and these electrons move here. And so this generates R, and so what you end up making is effectively an enolate. And so and the reason why you can actually do something very similar if you have a Grignard reagent and you use a bit of copper salts in there, like copper iodide. But typically what's going on is that you're actually making the Grignard, the cuprate in situ, and then it's attacking, and you're still doing the 1,4 addition. So organocuprates add 1,4, Grignard reagents add 1,2. And then the second step is the acid chloride gets attacked by the electrons move up, electrons move down, and you lose your chlorine. And so you end up with this you've basically trapped the enolate as an ester. Some of the more modern sort of reagents that you could use to do something similar would be, as I said before in class, like the trimethyl silyl group. Now, the difference between the two of them is the trimethyl silyl will be more sensitive to like water than the acetate. But it would add in the same fashion. So you'd make a silyl enol ether as your product. But what they've effectively done is they've trapped their enolate as something that is stable for the time being. And then the yield for the two steps is quite excellent, 84%. So the yeah, this is really good. Any questions on that at all? All right, if not, we'll move on to the next step. Okay, so what in the world is going on here? So what bonds do we need to break and what bonds do we need to make?
You have to reduce the double bond.
Okay, so this double, you're talking about this double bond here?
Yeah.
Okay, so are we, okay, when I think of reduce it, I think of we're adding hydrogen to it. Are we technically adding hydrogen to it?
No.
But something's definitely going on with it. Okay, so, okay, the bonds we need to make. What bonds are we making? We need to break.
We need to cut off the double bonded oxygen group there.
Okay, so we need to break. We'll use a red color here. We need to break this bond here. Is that the one you were thinking of?
Yeah.
Okay. We need to break carbon, oxygen, sigma bond. What other bonds are we breaking? We're making.
Bromine, carbon.
Right. We're making a carbon. Carbon, bromine, sigma bond. Okay, what other bonds are we making?
I really got to stop talking to a muted microphone. The double bond to the oxygen. It's kind of like a result of what's going on, but technically we're making it.
So a carbon oxygen double bond. So we're making this bond here. And we're making this bond here. Okay, right? Because we started with the sigma bond and now it's a double bond. So yeah, we're making a carbon oxygen pi bond, making a carbon bromine sigma bond. We obviously have to break this carbon oxygen sigma bond. And there's another major bond that we're breaking too.
The double bond.
Carbon carbon double bond, right? Pi bond. Okay, excellent. Now, if we look at the bonds which are being formed, and in particular this carbon bromine bond, how there's something special about the carbon that it's on, which is basically going to give a hint as to how this all works.
Are you talking like sp2?
Okay, it's certainly an sp2 carbon, right? But there's its location is important. So this
okay.
So this pi bond here is going to be the draw a bromine molecule. So bromine, remember, is an electrophile. So if this, let me erase something here.
It's gonna attack the double bond, and you should get like bromine cis to one another, or trans, whichever is opposite.
Okay, right. So one thing is clear is we get bromine on one carbon, but there's still oxygen on the other, right? So if this was an isolated double bond, we would end up with, yeah, bromine, and all of the groups on it. And they'll be trans to one another. That's correct. But notice that the other carbon doesn't have a bromine on it at all.
I did notice that.
Was it kicked out as a result of the carbonyl forming?
Okay, so yes, now that's okay. So there's two ways you can think about doing this. Okay, so the first step is, oh yeah, so like if you had this, and you had, say, oxygen with, I'll put a negative charge here. If this comes down, you could boot that out, and you would end up with a product over here, right? Okay, now I'll just erase that for a second. Okay, now so we want, oops, wrong direction. What's the best way to say this or suggest this? So bromine's the second step. Bromine is going to be the electrophile, which means that this carbon here is nucleophilic, and nothing seems to be going on at this carbon. So I guess my question is, the breaking of, oh, darn it. So the formation of the carbon bromine is going to be in the second step. The formation of the carbon oxygen, this might be a question mark as to when that forms. Breaking the carbon oxygen and breaking the carbon pi bond. Well, if we're forming the carbon bromine in the second step, then this has to be the second step. So the thing I've got in red, what's going on effectively in the first step? So methyl lithium, this is CH3 minus, think of it as like just, technically it's a covalent bond, but just think of it as CH3 minus. What do we know about CH3 minus?
Strong nucleophile.
Yeah, it's a strong nucleophile, it's a strong base. Okay, so we've got here, our ester has got a positive charge. So if this was to come and attack the ester, these electrons would move up and you'd form your tetrahedral intermediate. Then these electrons would move back down and we've got a leaving group here, right? The rest of the molecule. So in this first step, what we should be making as an intermediate would be negative. And then the rest of the molecule R. And we've got lithium as a counterion, so it's entirely possible that this oxygen could be bonded to a lithium. But if you think of a resonance structure of this, we draw a resonance structure. We use a different color, purple. I'll just call this R. Now that carbon, that this is technically over here, you call this the alpha carbon, right? Because it's right beside the carbonyl. You've got a negative charge here. So what you're actually doing in the first step is you're regenerating that enolate. And I've drawn this with a negative charge, but it could be bonded to the lithium. So you've got an enolate, and then this is going to attack the bromine, and that's going to form the bond with on the alpha carbon, which is interesting. Now, I've got another question to ask, but I'm going to erase a bunch of stuff in a second. So when we were doing the review of enolates and enolate equivalents, one of the reactions that was common was that if you took a silyl-enol ether and you reacted it with methyl lithium, you would generate the lithium enolate R. So if you do this like methyl lithium with a silyl-enol ether, you're going to make this. So it's a similar type of reaction, but you can do this. This is why I sort of flagged that earlier. The yield might be better. I don't know. They might have tried it. They don't mention, in one of the things which is really interesting is that in a lot of the more recent papers when it comes to synthesis, people will spend an awful lot of time talking about stuff which might not have worked. Because a lot of man hours would have gone into it. And they'll show a whole bunch of like, this is what happened. Sometimes in some of the older papers, discussing things that tried and failed isn't quite as common. although some of them do, but it's not necessarily brought up a lot. Now I'm just gonna erase a bunch of this stuff because I've got another question to ask everybody.
Isn't that sort of like the whole purpose of doing papers in the first place, though, is to be like, yeah, this didn't work.
Well, it would be nice if if there was such a thing as a paper, like a journal of failed of failed chemistry, right? That would be really helpful. Like, because then,
Or like your standard lab report having like a section about failure. Like your paper would have a failure section.
yeah, that would be a good thing, I think. Okay, my next question is, why 1 equivalent of bromine?
Because you don't want to start messing with that triple bond over there.
That's right. So the triple bond will react with bromine, and it will actually react with bromine twice, and you could actually end up with a thing where you got the tetrabromide. Good. Okay, so yeah, so bromine will react with the triple bond. Okay, so next question then. What's an equivalent of bromine that could have been used as a source of Br plus as well?
Could you use Br plus?
There's another reagent which is a source of Br plus, or I'll put it in quotation marks, or Br radical.
Is it NBS?
Right.
Remember.
That's right. NBS.
Nitrogen compound? Yeah.
This one. So the advantage of NBS is that it's a crystalline solid. And so if you're doing this on a small scale, bromine would be kind of difficult to, like, because you guys were using those, everyone's used the 1 milliliter syringes, right? And it'd be easy to add excess bromine, because bromine weighs so much that if you're doing it on a relatively small scale, it'd be hard to control it. But NBS, it's a crystalline solid, you can weigh it out. So it would be easier to manipulate than, say, Br2. But yeah, this would be another alternative for this reagent here.
Would Br2 be like, because you're doing large batch, it would matter less, like what you're putting in a system, like if you're doing this industrially? Like, is that why?
If you're doing this industrially, you'd probably want to use Br2, actually.
Okay.
Because sorry, I just got distracted. Well, the amount of waste associated with it, if you're using bromine as your electrophile, the waste would be bromide, which would be water soluble, and you could deal with it. Here it'd be the succinimide atom, which would be solid. I don't know we'd have to do the calculation of the weight. One of them, like if we're talking about the PMI ratio, that would be one will have an advantage over the other, I'm guessing. I have to do the math on it though. Okay, let's erase this stuff. Let's go on to the next slide here. Okay, so now the next step is that they are generating an enone here. And so what type of reaction is this?
Elimination?
Yeah, this is just the elimination reaction. You've got proton over here, and they are just using a relatively weak base to eliminate it. And it's, yeah, so it's just an elimination reaction. Okay, so we've generated an enone, and now we're gonna set up the key step here. But before we do that, we've got to do couple transformations here. All right, so lithium aluminum hydride. Again, we've got a situation where it's 1, 2, 3, 4. So lithium aluminum hydride reductions they favor 1, 2. Now, somebody would have done a reduction with some other system which would do exactly the same thing here. What was that? So we're making here an allylic alcohol. Yeah, one of the reactions or reductions we just did involved enones to generate allylic alcohols. Does anybody remember who finished their evaluations? So if you take an enone and you use sodium borohydride, the product you end up making is just the alcohol. So you reduce it to the alcohol. But if you used a certain additive with it, you could get the allylic alcohol. All right, well, for those of you who haven't done your evaluations yet, it was the loose reduction, and there's a cerium, I think it's cerium trichloride is the additive that was put in there. But anyway, you'll see that later. I'll erase all of this stuff. So reduction, they make the allylic alcohol. And then the next step is here. Okay, so this is basically the key step of the entire synthesis. I'm just looking to see something and I can't see it. Okay, so we're gonna have to go through this slowly. First things first, though. Oh, wrong. Okay, so this is just looking at this sideways. I'm going to go back to the original slide here, though. So they're basically made the 7-membered ring and the other 5-membered ring in this step. Okay, but Okay. If we're going to unpack this, we have to understand what's going on. So the compound in blue, what type of compound is this? If you had to classify it as something. So we've got a carbon bonded to 3 fluorines, electronegative.
Is it not just a carboxylic acid?
Right, so this is a carboxylic acid, so this is basically an acid. Okay, yep, so it's an acid. Okay, so, get out of that. So that means that our compound here on the right, the allylic alcohol, is going to be our Lewis base. And so the first thing we're going to do is we are going to protonate this alcohol. Okay, now if we protonate this alcohol, what's something which what can happen when you protonate an alcohol?
Can get removed.
Right, so it can leave because it is now a decent leaving group. So let's make that leave for a second. And so I'll try to draw this nicely. Okay, so positive charge. We've got our and the interesting thing about this positive charge is that it is stabilized how?
Double bond moves.
Right, so the double bond moves when it is stabilized by resonance. Okay, so right, so let's move this over. And so this is a resonance stabilized positive charge. Now, what's interesting here is that although I've drawn this as on the 2 different carbons, this molecule is symmetric, right? So if I'd drawn this out as a, maybe I'll try to do that. Let's draw this in another color. 1, 2, 3, 4. 1, 2, 3, 4. And because this double bond can exists here and here, basically this molecule, if you divide everything right down the zigzag, these 2 methyl groups will eclipse each other. It's a completely symmetrical molecule. Okay, and so now, what if we start labeling carbons and this sort of stuff? We're going to see what happens. Okay, so now, where are we going to number carbons from? Let's number carbons from our starting with, I'm going to erase a couple of things here. 1, 2, 3, 4, 5, 6, 7, 8. And I'll call this 9, and I'll call this 9 prime, just because if it's symmetrical, like if we ignore all these other things, so this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 primed. Just so it's clear. Okay, now if this is our product, and we've got a carbocation here, this OH group is probably going to result in the last step here from, if we drew the entire structure out, I'm not going to draw the entire thing, but this carbon here would be this carbon here. It's probably got a positive charge, and it's the water which has come in and attacked that positive charge because water left earlier, right? So that's probably where that hydroxyl group came from. Okay, so now we need to label our final product with the appropriate numbers, and we're going to see where the various bonds are made and where the various bonds, where the various bonds are made, really. So one carbon is clear, which sticks out. Which carbon is that? Which is just obvious that it has to be the same carbon, which you could put a number to. Like if you had to bet, if you had $1 million and you had one bet, you wanted to guarantee that you're gonna not lose your $1 million. Out of all of the carbons in this numbering here, which carbon are you certain of you can put a number to in the product over here?
7?
7, exactly, 7. 7 is the one because it's got the dimethyl group on it. So let's label 7. Okay, and that would mean that this carbon here, where the OH group is probably carbon 8, right? And if you go backwards, 6, 5, 4, 3, 2, 1. And that means that if we call this 9 and this 9 primed, we can see that the bonds are being made between carbons 9 and 9 prime, which is where the positive charges are when we do the two resonance structures, and carbons 2 and 3. And what were on carbons 2 and 3? Oh, the double bond, this triple bond, right? So once we have oh no, what's happened? I'm just trying to erase something here. I'll erase these. So what we have going on is that, okay, so this positive charge, that means that this part of the molecule is going to be the, oh, darn it. That this part of the molecule here is the electrophile, and this is going to be the nucleophile. And what we'll see is that if we have this attack, and let's say it attacks, and carbon 2 attacks carbon 9 primed, or sorry, sorry, carbon 3. Yeah, carbon 3 attacks 9 primed. That means that we're going to get a positive charge on carbon 2. Right? So gosh, I did draw this out somewhere. Let's draw a long chain here. 7, 6, 5, 4, 3. And then this double bond is going to come and attack way over there. And that's going to make our final product. Now, drawing things out like this looks like, and then when you do that, what's going to be left over is your 5-membered ring is going to have a positive charge on that carbon in the middle. And this will be bonded, and it's all going to be connected together. So now the question is the transition state of how this triple bond interacts with the corresponding allylic carbocation. So I think on the next slide, it's easier to show this. So this is our final product here. If we draw out our carbocation, and 1, 2, 1, 2, 3. I'm missing a carbon. And we would have a carbocation here and a double bond here. Now the trouble is with this is that the way I've drawn this part of the molecule should be flatter. But I just drew it like this just to show the structure of, where is this? The structure of that this shaped the way it is. So this would be flatter. And so if this attacks here, then the corresponding, this will develop a positive charge, and then that'll attack there. And that's basically how the whole thing worked. Now, come on, little thing. Where's my drawing? Oh, stop that. Oh, I'm trapped in Zoom mode. Turn that off. Stop that. Why is that not working? Okay, I'm just going to stop sharing for a second so I can get this back going. Oh, God, right. Why is that not working? God darn it. Okay, let's take a 5-minute break. So I can sort out my computer issues. Plus, we need a break anyway because it's a 2-hour class. And I'm stuck in here. I might have to turn everything off and restart. So